In this lesson, you will learn how to balance chemical equations. But before we begin, two things. One, this is a video recording of a Pear Deck, but obviously it will not be in Pear Deck mode. And second, we're going to do a little review before we begin. When we look at a chemical reaction, remember we have two sets of numbers. We have the coefficients out front, which basically show us how many atoms or molecules are reacting. And then the small numbers we call subscripts, and that's how many atoms are in each of the particles. Additionally, on this slide you see the red side are the reactants, which are the substances that react with one another or go into the reaction. And then on the right side after the arrow are the products, which are created by the process of the reaction. So just in review, the coefficient in front of the particle indicates how many particles are reacting or how many are being produced in the case of the product side. If there is no coefficient, just know that there is only one particle. The subscript, which is after the element symbol, indicates how many atoms of that particular element are in one particle. If there is no subscript, it just means that there's one atom. The chemical reaction would then be read. Two molecules of hydrogen react with one molecule of oxygen to make two molecules of water. Sometimes you'll hear the arrow referred to as the word yields. Moving on. Additionally, what you may see is some letters that indicate the state that the substance is in. What do you think this G stands for? So when you write the state, G stands for gas. These are the possible states that you might see in reactions. G for gas, L for liquid, either a pure element or a compound that's in liquid form. S for solid, AQ for aqueous or aqueous, when an element or compound has been dissolved in water. Now if you'd like, you can do a little practice to write this reaction in words. And you can pause for a moment to give it a shot. This would read, one molecule of nitrogen gas reacts with 3 molecules of hydrogen gas to make 2 molecules of ammonia gas. Note that instead of saying any particular gas, you can also say gaseous, etc. So for example, you might say gaseous ammonia and gaseous hydrogen and gaseous nitrogen, for example. But before we continue, for a little review, what kind of reaction would you say this is? Before you keep going, make sure you take a stab at it, because the answer is, this is synthesis. You have 2 individual substances or particles coming together to make one. Now moving on, in order to get to the balancing piece, we need to review the law of conservation of mass, or matter, which states that in a closed system, matter or mass cannot be created nor destroyed, only gets rearranged even if there is a chemical reaction. And for a little review, feel free to watch the video in the Ring of Truth where we saw a series of chemical reactions taking place in a closed box, yet the mass did not change. Let's take a look at a reaction here. I would suggest that you try particle diagrams to represent this chemical reaction, and make sure that you use unique particles to represent each type of atom, not just each type of molecule. So here, take a moment to try to draw particle diagrams for each of the substances that are reacting, and take note that, for example, carbon and oxygen, even though they are combined, they are unique elements, so you should represent them uniquely. I'll move on to the next slide where you'll see an example. So here we have copper and oxygen represented by differently colored and sized particles, because their atoms are not the same size. And then you have a diatomic hydrogen. That's why there are 2 hydrogen atoms, if you will, joined together. Remember that hydrogen is quite small. This then yields copper. So there's our single atom of copper, and then here is water. So our oxygen with the 2 hydrogens. So that's how we could represent these with particle diagrams. And as you begin to balance chemical equations, you'll see that drawing particle diagrams can be very helpful. So now let's go through how many of each type of atom is present on each side of the equation. Hopefully you came up with 1 copper, on the reactant side, 1 oxygen and 2 hydrogen atoms. And so that's just staying on the left side of the arrow, doing some simple accounting, how many coppers, how many oxygens, how many hydrogens. And then you do the same exercise for the right side of the arrow. These are our products. We see just 1 copper, we see 1 oxygen, and 2 hydrogens. So to move on, does this follow the law of conservation of mass? Do we have the same number of each type of atom before and after the reaction? And if you said yes, then you are correct. This does indeed have the same number of atoms of each type on both sides of the reaction. And before we move on though, what kind of a reaction is this? Make sure you take a stab at that before you continue with the video. And if you said single replacement, you would be correct. In this case, the oxygen is replaced by hydrogen. Pardon me, the copper is replaced by hydrogen in order to form water. Second example. Here again, try to use particle diagrams to represent the chemical reaction below, and remember to tell the different atoms apart by using different colors or patterns, and make sure you join your unique atoms together in the appropriate fashion. So here we have copper, and here I go, carbon and oxygen joined together, and then we have a diatomic oxygen molecule and carbon dioxide. Now note that carbon and oxygen are quite similar in mass, so we can draw them with the same size. So go ahead and count up the carbons on the left side and the reactant side, followed by the total number of oxygens, and then do the same on the right. Go ahead and pause the video so you can accomplish that. So here we have an obvious imbalance in our number of atoms. Our carbons are definitely balanced, but our oxygen atoms are not. So this does not follow the law of conservation of mass. So we couldn't just magically lose some of our oxygens out of this reaction. They had to go somewhere. So this is where we're going to try to figure out how to balance this equation. We'll start off with some particle diagrams, and then ultimately you could probably walk away from that visual representation and just look at the numbers. So as we said, there's more oxygen in the reactant side than the products, and as it's written, mass has been destroyed, and we know that that's not going to happen. So here we need to figure out a way to remedy that problem. So the way that we fix this problem is by drawing in additional particles in the diagram to make it follow the law of conservation of mass. But don't change the formula. We couldn't just go in here and add in another carbon. That wouldn't make sense. Or add in another oxygen. That wouldn't make sense, because then you're changing the type of substance. But what we can do is add in more of each of the molecules as needed. So don't change the formula or type of particles, just how many particles react. So if you notice here, what's been done is an additional carbon dioxide has been added. Sorry, an additional carbon monoxide has been added, and an additional carbon dioxide has been added. So now when we go through and we count our number of carbons on the reactant side, we have 2 of them, 1, 2. And the oxygens, we have 1, 2, 3, 4. So we have 2 carbons, 4 oxygens in the reactant side. Obviously that's an increase from previously, but let's take a look at how our adding of a carbon dioxide helps on the product side. So we have 1, 2 carbons and 1, 2, 3, 4 oxygens. So now we see that our carbons and our oxygens are in fact balanced. So how do we represent this back in our chemical equation? So what we're going to do now is just simply add in some coefficients. So we said we needed two particles of carbon monoxide, so we would put a 2 in front of the CO2, carbon monoxide. We did not add any more oxygen molecules, so we'll leave that just as it is. And then we'll come over here to the CO2, or the carbon dioxide, and put a 2 there as well, because we have 2 of those particles. So now we know that this is balanced. But before we go ahead and move on, let's consider what kind of a reaction is this one. And hopefully you came up with synthesis, where carbon monoxide and oxygen join to make carbon dioxide. Now, when balancing chemical equations, remember we're changing the coefficients in the chemical equation to make it follow the law of conservation of mass. We call that balancing the equation or balancing the reaction, since a chemical equation shows a chemical reaction. But remember, very importantly, never ever change the formula of any elements or the compounds in the reaction. Only change the coefficient, the number of particles. So in other words, you can change the big number, but not the little numbers. Here are some simple strategies that you might want to jot down for balancing. 1, take a chemical inventory. Draw a table like you saw in the previous slide, especially for more complex reactions. Some are pretty straightforward and you don't really require much in the way of inventory, but some do get a little bit more complicated. 2nd, if only one element is unbalanced, start with that one. Don't make it overly complicated. Start with which one stands out. 3, otherwise balance the least common elements first. So the ones that you don't have as much of, those are the ones that you should start with. Lastly, leave any elements that appear in their pure form for last. Hopefully those are good tips. Let's move on for a couple of practice problems. Solid mercury 2 oxide reacts to produce liquid mercury and oxygen gas. Now you should be fairly decent at naming at this point, so you might have been able to come up with this equation yourself, but here it is. So HGO reacts to make mercury and oxygen. So some relevant strategies. 1, take a chemical inventory. You might be able to do this, a mental inventory on this one. And then 2, remember if only one element, in this case oxygen, is unbalanced, start with that one. We obviously see that the 2 mercuries are balanced, but the oxygen are not. But before we balance it, what kind of a reaction is this? Hopefully you said decomposition. Okay, so we are trying to come up with the coefficients that belong in front of these substances. So I would start with some particle diagrams for just a little visual. You could do a table. Here's a visual for you if you want to look at mercury 2 oxide giving way to some mercury and some oxygen. We can see that the mercuries are out of balance. So if we add another one, we're closer, but not quite there yet. Looks like we've got 2 of those guys. We might need a couple mercuries, and then we should be balanced. So here's another way to take a look at it. You could just start with your table, and you would note with your inventory that you have 1 mercury, 1 oxygen, and then you would be left with a mercury and 2 oxygens. So we need to make these 2 balance, the 2 oxygens balance. And the way that we can do that is by adding the coefficients in front of mercury oxide and mercury. Let's take a look at one more example. Liquid ethanol or alcohol reacts with oxygen gas to produce carbon dioxide gas and water vapor. And here's your equation. So some strategies that would be great to use here. An inventory would probably be good. This is more complex. You might also notice that you have oxygen spread out, and so you don't want to miss those, even though they're in 2 different substances on both sides of the equation. You might also start with your least common element, which happens to be carbon, and save your pure element, that is oxygen, for last. But again, before we balance, what kind of a reaction is this one? Hopefully you said combustion. Okay, let's start with some particle diagrams. So first of all, that's a little bit more complex, right? We've got some carbons, these carbons, and oxygen here, some little hydrogens. Here's your oxygens again, and then your CO2 and your water. So we can see that we're out of balance, that we're going to need to add in some more molecules or to help us balance this equation out. Now if we add in our CO2, remember we're starting here with our least common element, maybe we can address that. we only have, we have 2 atoms of carbon on the left side of the reactant side, but we only had 1. So by adding 1 more carbon dioxide, now we have 2 carbons. That looks pretty good. But now we've got 2, 4, 6 hydrogens and only 2 on the right side. Remember, we're going to save that oxygen for last and see if we need to do anything. So if we add some more waters, well, there's our coefficient for CO2, now we've got 2, 4, 6 hydrogens in the reactant side and 2, 4, 6 hydrogens on the product side. Okay, looking pretty good. And so now we need to account for our oxygens. So in this case, we have 1, 2, 3 oxygens on the reactant side, 2, 4, 5, 6, 7 on the product side. So that's kind of funky because we have some odd numbers. However, if we add some more diatomic oxygens, we can probably make these guys balance out. So again, we had 2, 4, 6, 7 on the right side and 3 on the left. So if we add in a couple more diatomic oxygens, so a total of 3, now we have 7 oxygens on the reactant side and 7 on the product side. That is balanced. Another strategy is to use our inventory table. And so here we have counted our atoms on of each type on the reactant side. And just be careful here. The carbon should be pretty straightforward, but maybe on hydrogen, if you only counted 5, look really carefully. There's another one right here. So, and the reason why it's written this way is because this OH forms a functional group, and that's just how they bond together. So we actually have 6 hydrogens on the reactant side. And then on the oxygen side, maybe you miss this guy, maybe you miss this guy, but you've got to add it all up. So there's 2 here plus the 1 here. That's where we get 3. And then on the product side, the carbon is pretty straightforward. The hydrogen is pretty straightforward, but you do see oxygen in 2 different places. So you need to make sure you add those together. And so by some simple math, you might ultimately come up with the same answers as we did with the particle diagrams. I try to, sometimes I'll cross out a coefficient and add my new one to the right of it, and then I will try it out. I'll put it in front of my molecule, and then it's almost like FOIL in math, where you take that, that coefficient and you distribute it into your, I guess it's not quite like FOIL, it's more like just distribution. Distribute it throughout your molecule and see if you've gotten your number of atoms balanced. All right, that is all. Hopefully that was helpful in learning how to balance equations.